Hello again. So in this video, we're going to work through the electric field from a disk of charge. And again, I want to center this in the XY plane on the origin, the XY plane. And we're going to look for the electric field at a distance Z above that disk. It's very similar. Geometry, strategy is the same as for a ring, really. You just have to adjust things because now a disk is a 2D shape. So let's go through and see how this plays out. So the geometry looks kind of similar. We've got a disk. Draw my axes. So I've got X, Y, and Z. And we want the electric field up here above the disk. We're going to say that the outer edge of the disk has a radius R. But interior points have, they would have different radii typically. So these points here are not all at the radius of a typical little piece inside wouldn't be capital R. This little chunk, if I were to kind of draw it out, you know what, I'm going to move it just a little bit better for me. How about I move it down here? I think it'd be a little bit better. This one would have, relative to the origin, we'll use a lowercase r to talk about the radius where it is located. And it also has an angle, of course. So that's fine. So this is a disk. It's clearly a 2D shape. And that means that the sort of geometric, differential geometric thing we should be thinking about are areas. So the area would be, the baby chunk of area would be dA. And if you remember, in polar, we're going to use polar coordinates. I'll add sorts here. We're going to use R and theta. I'm using lowercase r to remind myself that R is a variable now, not a fixed number. dA is the area of a little chunk of area. And we worked that out before. That equals R dr d theta. Okay? Great. Now, it's a 2D shape, so we should have a surface charge density, which means that we can say that dq is sigma dA, which equals sigma r dr d theta. Now, like in the last example, I'm going to assume sigma is constant. So we're assuming that the charge is spread uniformly over this disk. Again, the setup is the same no matter what. You just have to do the calculus, right? So do the calculus, and if sigma varies, then obviously the formulas you get will change a little bit, but it's something you guys can't handle. Okay, so we've got dq, and now, okay, so this little chunk is located at a position R and an angle theta. But if you think about it, that means that the observer here, that person's up here along the z-axis. That's just going to be z hat again. And then the position of a little source of electric field is it's a very similar formula to what we have for a ring, except now the radius we use is the variable r because that's where the charge is. So that's just going to be r cos theta x hat plus r sine theta y hat, piece of cake. RSO, again, looks very similar. We really just are switching capital R for lowercase r. Now so it's final minus initial, z z hat minus r cos theta x hat minus r sine theta y hat. And then the magnitude of r s of o, it's a very similar looking formula. That's going to be z squared plus r squared to the 1/2. And then the unit vector, RSO vector, equals RSO, or I guess it's RSO hat is RSO vector divided by magnitude RSO, which is just going to be z hat minus r cos theta x hat minus r sine theta y hat, all divided by z squared plus r squared to the 3/2 power. Piece of cake. All right. So at this point, let's work out the charge. Okay, so let's kind of start with a trivial statement here, that the charge equals the sum of all the little bits of charge. That's trivial. It's true, but it's not very useful. And we want to turn that into an integral over areas. So that becomes the integral of sigma dA, almost there. And then I want to write that as the integral, because I'm in polar coordinates, dA is r dr d theta. And now I really should probably be more careful here. So I have a double differential, right? I have two differentials there. So I really should have a double integral sign. And you can, for this one, you can do the integrals in any order. Let's do the r integral first. We'll integrate r from 0 to big R. We'll integrate theta from 0 to 2 pi. Okay. So when I do the interior integral, that's just going to give me sigma r squared over 2, so 0 to r, which is a sigma capital R squared over 2. That's inside. So then next I have to integrate it over inverse. And that's just going to give me a factor of 2 pi, which cancels with 2. And I'm going to get pi r squared times sigma, which of course it has to, because the charge density is uniform. It's going to be the area times the charge density gives me charge. But it's good to see that it works out. Okay, so now let's follow similar lines. We're going to think about this disk as a collection of point charges everywhere, evenly, uniformly spread out. Okay, so we're going to say the electric field is the sum of all the small electric fields coming from every little bit of charge. And I can use Coulomb's law for each little point charge. So that's 1 over 4 pi epsilon naught. Times, just a second here, I just have a moment of panic. I forget to write 4 pi epsilon naught. Did I write it? Oh, I did. Good. I was afraid I forgot to write that above. So we're good. Sorry. Continuing. Okay. So the electric field, I'm using Coulomb's law. So remember that says that dE for applied to differentials, that's going to be dQ over 4 pi epsilon naught r hat SO RSO squared. So we're going to have dQ which can be expressed as in terms of the surface charge density as 1 over 4 pi epsilon naught integral sigma r dr d theta, or RSO squared z hat minus r cos theta x hat minus r sine theta y hat, all, oh, tell you what I'm going to do. I'm just going to do this, I'm rewriting this here. I'm just going to write this out in terms of r and z right now. So the numerator gives me the magnitude of the vector squared here, and then there's a hidden factor inside the unit vector. So I end up with r squared plus z squared to the 3 halves power. At this point, it should look sort of similar to what we had for a ring. The main difference is being a double integral in sigma, because we're in 2D, and then we have lowercase r's instead of capital R's. And that's simply because here the radius can change as you move around inside the disk. Okay, now, most of the time in our class, you can do the integrals in any order you want. And you can here too. But one way is clearly easier. What I would recommend is to do the angle integral first, because we already saw with the ring example that it makes the x and y components go to 0. So that makes, it just cleans it up, right? So we're going to do that first. We're going to change color to show you what's a choice. You didn't have to do this, but so we're going to do theta integral first. Because it's easier. And it's really not. You don't have to, but you just, if you don't, you're going to make your life a little harder. Okay. If you do that, like with the ring example, these are both going to integrate to 0, doing the angle integral first. So we're going to be left with the electric field. And notice the other terms, the z component is constant, independent of theta, not like the ring example. So what I ended up with is just an overall factor of 2 pi. Sigma is a constant, so I'll pull that out. Constant up front. And then I have, so the 2 pi here comes from the integral, the theta integral. So now I'm left with the r integral, which is integral of r dr over r squared plus z squared to the 3 halves. Okay. And that's an integral we have to do, and we're going to integrate from 0 to capital R. So this is a integral you guys can do. We're going to use a u sub. We're going to say u equals r squared plus z squared. So we're going to say du equals 2r dr, or equivalently, r dr equals du divided by 2. Just rearrange. So look, this bit is the same as that, and this bit is in there. So we get that the electric field is the integral of du over u to the 3 halves power. And then now I've got all these constants. So I'm going to put all these constants together. I have the half here, and I'll just crop out front. So I'm going to get 2 pi sigma over 8. I don't know why I'm carrying this around. I should simplify it. Okay, whatever. 8 pi, that's not that. Let's clean it up next time. Next line. Now, what about the limits of integration? I'm integrating over u. When r is 0, u is z squared. So the lower limit for u is z squared. On the other hand, when lowercase r equals capital R, the upper limit for u is r squared plus z squared. You see how I did that? I looked at the limits written in terms of r, and I had used my equations to convert them into limits in terms of u. All right. So so now we're pretty much there. The electric field. Oh, hold on. Forgot one thing. You know what I forgot? If we were in person, I'd complain you didn't point it out to me. I forgot to write ZZ hat. I dropped it. So there should have been a Z hat here. I forgot. I'll highlight that. Well, you see. Okay. I just forgot to write it down. It's a constant. It pulls out of the integral. Nothing to it. All right. And that means I also have a ZZ hat here. Just a constant vector. So now, right now, as it stands, I have sigma over 4 z hat over epsilon naught. And that's the integral I have right now. I think I've got all the little pieces. Before I pull the trigger on this, let's just check. Good. That 2 pi came from the integral, z hat, got it. I think we're good. And then I have the integral du. Well, that's a power law integral. So I add 1 to the exponent. So it becomes u to the minus half and divide by minus half. This becomes 1 over minus a half, right? Because that's my new exponent, times u, the minus half. So that's 1 over the square root of u, evaluated between z squared and r squared plus z squared. Dividing by half is multiplying by 2. And the minus sign has the effect of just switching the limits of integration. So I end up with sigma z hat over 2 epsilon naught. Cancels, the 4 cancels against, a little bit of the 4 cancels against the half. And then I get 1 over, and because I'm going to get rid of the minus sign, I'm going to put the lower limit first. I'm going to write it as this square root of z squared minus 1 over square root of r squared plus z squared. Now you might say, what are you doing? Why don't you just call that z? It's not quite z, because when you square something, you get rid of the minus sign information. And so actually, this is the absolute value of z in the denominator here. So this is sigma z hat over 2 epsilon naught times z over magnitude z minus z over square root of r squared plus z squared. Now, this is the right answer. This term, let's kind of go through these here. And I'm just going to leave it in terms of sigma because of what I want to do next. Because I want to take the limit as the ring, or sorry, as the disk gets really big and sigma stays constant. But if we wrote it in terms of Q, I mean, that's just algebra. You can do that if you want. Okay. This term right here is actually, if you think about it, z divided by the magnitude of z is simply the sine of z, not trig sine, but it's the actual sine of z. So if Z is positive, it gives +1. If Z is negative, it's -1. Okay, that makes sense because, so here's your disk. You got charge. If you're up here for positive Z, the electric field is going to be going upwards. If you're down here for negative Z, it's going down. That's the sign business. Okay, and this term is it's just a contribution we have, and it sort of knows about the edge or the kind of shape of the disk, but really I don't have a better interpretation. Maybe I should try to come up with one, but it is what it is. For us, and this is, okay, it's a nice application of what we've been talking about, but what I really want to highlight is what happens when we take the limit for a huge disk. Huge disk and constant charge density. So what I'm imagining is charge uniformly sprinkled to infinity in at the XY plane. That's really what I'm looking at. So to get to that, what we should do is take the limit as it's sigma constant and R goes to infinity. Now, just want to note, if you think about it, that means the charge, which is sigma times pi R squared, would go to infinity. But if you evenly spread out charge forever, then the total charge is going to be infinite. So that means you can't really have this configuration. You can't have fill. So in the universe, there are no infinite sheets of charge. But if we're modeling behaviors or features that an electron will see, electrons are tiny. So something like a postage stamp, that's all, might as well be infinity as far as an electron is concerned. So this is a good model for many different configurations. Okay. And what we get is the following. So in that limit, if we look up here at the formula, if R is big, the denominator gets big. This means the fraction gets small. And we're left with just the first term. And that's what we have. What we get is the electric field for an infinite sheet equals sigma over 2 epsilon naught times z hat, and it's I guess I should multiply by the sine of z plus or minus 1 times z hat. Or usually people just say the electric field for an infinite sheet, they just write the magnitude is sigma over 2 epsilon naught, and then you can just look at it and see whether it goes up or down. Okay, this is a really useful formula. It's one that, quite frankly, if you just remember it, sometimes it helps you if you get lost in a problem and you kind of know that, well, it's got to work out to this. So it kind of knowing the answer sometimes helps you a little bit. Make a confession. As I was going through this just right now, when I got this minus sign there, I thought, I don't remember that minus sign. And then how did I know that I was right? Well, because I could see what was going to vanish, and I knew that that front term was spot on because I know the answer for the infinite sheet. So it's useful. Okay, the important thing about this is that it is constant. Right? So what this means is that if you have an infinite sheet of charge, the electric fields vectors you get are They don't change as you move sideways. They also don't change when you move away. If it's really an infinite sheet, then they're constant forever. They fill the universe with the uniform bath of electric field vectors. Now, real in the universe, that's not really going to happen, but it happens well enough on small scales. We haven't talked about field lines yet. It's killing me to write all these. All right, it'll get a lot easier to draw these things when we get field lines. It's coming up next. Okay, so the only difference is if you're above the sheet, it's upwards. If you're below, it's downwards. But you can just look at it and see that. And here we have the charge in the middle. So it's constant. It fills the universe. You know what this is like in a gravity problem? This is like saying that G is always constant 9.81 meters per second squared near the Earth. And we said that it was the same 1 meter off the ground, or 2 meters off the ground, or 3 meters off the ground. If you move sideways, it was the same. In fact, it's the same thing. What happens with the Earth is in real life, the whole thing, the full answer is complicated. But if you zoom in near the Earth's surface, the Earth is approximately an infinite flat plane for our purposes, and the gravitational field becomes constant and uniform. So that is a finite disk of radius r, and then this is the formula you get when you take the limit for an infinite disk. We will see this answer pop out again when we learn about Gauss's law. So try to remember it, and I'll point it out to you when we get there. All right, talk to you next time.